Alright, so the video probably cut off, so don't worry. I'm going to kind of back up and review a little bit. We were dealing with just this function in general that you're going to run into often in calculus problems, especially in these upcoming sections. And it's the absolute value of some quantity over the same quantity without an absolute value. And that is always equal to the piecewise function -1 where x is less than a, and 1 where x is greater than a. The graph will always look like this graph up here that I was just starting to graph. So in our particular case, the a is 0. So this whole function, the absolute value of x over x is equal to -1 whenever I put a, when x is less than 0, because that would make the bottom negative and the top positive. And +1 whenever, and those are open circles, whenever it's greater than 0. So the limit as x goes to 0 does not exist here because of the limit as x goes to 0. They're different. The limit as x goes to 0 from the positive is not equal to the limit as x goes to 0 from the negative. That's the reason why. All right. So the next problem, I think we're really just discussing finding the limits, okay? Finding the limits as it has to do with continuity. So this one looks like a problem we've done before. This is number 13 in the book. And really, if I think so, I'm just going to approach it like I have before. So I'm going to multiply the top and bottom of this fraction by what I would need to do, what would the common denominator be if I were getting one here. And that happens to be x plus delta x times x. So I'm going to multiply the top and bottom of this fraction times this. Notice I'm not multiplying it out at all. All right, so on the top, if I distribute this times this is on the top, and this is on the bottom, okay, minus, this is on the top, and x is on the bottom. So that's just the top. All over the bottom, I'm just going to write x delta x and x plus delta x. And I'm still needing to find the limit. All right, so I'm writing out every little step here. So now the next thing I'm going to do is simplify these two things. These cancel, and I get x on top. These x's cancel, and if I distribute that negative, I get minus x minus delta x. I've still got the same thing I had on the bottom. Again, I'm just using algebra techniques like we have before. I haven't found the limit yet. So now x minus x cancels. So on the top I have negative delta x. Since that's the only thing on the top, that delta x will cancel with that one. So now I'm actually just taking the limit as delta x goes to 0 from the negative of -1 over what's left on the bottom is x times x plus delta x. All right, so now if I substitute 0 in for delta x, I get -1 over x times x, which is x squared. So that's the limit. If I can use the algebraic methods from before or substitution, I still do it even though it's a one-sided limit. All right, I'm trying to pick out difficult ones. I want to find the limit as x goes to 2, where f of x is this horrible mess here, and it's just as x goes to 2. So there's a difference. One-sided limits I can a lot of times find unless it's undefined. So like this example of this piecewise function, this is a two-sided limit. So what you have to realize is that this function here, okay, is two pieces. And you don't even have to you don't have to graph this to realize that at the 2 is where this graph may or may not meet. And all you have to do to decide whether or not they meet is put 2 in here and 2 in here. The limit as x goes to 2 from the left, the limit as x goes to 2 from the left of this function, we'll be putting into the one where it's less than 2. That's just a less than, I scribbled out the or equal to. So less than 2 means the same as that. So I would put the 2 into this function from the negative. And then define the limit as x goes to 2. In other words, I'm seeing if the limit is the same on both sides, okay? Then I would put it into this one because the right-hand limit is from above, so greater than 2 is above. So all I have to do is plug 2 into here. Okay, 2 squared is 4. That negative keeps it a negative. Plus 8 minus 2. So that's going to be negative 4, negative 2 is negative 6, plus 8 is 2. That one's 2. If this one's also 2, then that's going to be the limit as x goes to 2. If this one is not 2, then the limit will not exist because there will be different limits on both sides. So now if I put 2 in, okay, from the negative doesn't mean put a negative 2 in. It means from below it, which we know since this function is defined where x is less than 2, that's the from below. So I just put 2 in. So 2 squared minus 8 plus 6. So that's 4 plus 6 is 10 minus 8 is also 2. So the limit, since both of these are the same, the limit is 2. If they had been different, the limit would not exist. Okay, so this one is a function. It's not asking for, it's the same type of question, but it's not asking for the two-sided limit. It's asking for the one-sided limit from the positive. So our job is to pick out which one of these pieces of the piecewise function represents from the positive. Above 1. It's this one. This is from the positive, above 1. So I need to just use substitution. So the limit as x goes to 1 from the positive of 1 minus x. So put 1 in and you're going to get 0. It doesn't matter if this one from the other side is not the same because we were only asked to find the one-sided limit. It is a waste of time to look at the other one. All right, moving on, number 20, the limit is x goes to pi over 2 of secant x. I am just going to try straight up substitution. Sorry you can't see that yet. Number 20, the limit is x goes to pi over 2 of secant x. If I just plug that in, the secant of pi over 2. All right, well, here's my ordered pair. Here's pi over 2 right here. Okay, here's my unit circle. Pi over 2, the ordered pair is 0, 1. And this is the cosine, this is the sine. Secant is 1 over the cosine. So this is undefined. Which means the limit as x goes to pi over 2 of secant x does not exist. Because if you remember the graph of secant or cosecant, they've got like the little u thingies. Okay, and then another little u thing down there. So that limit just doesn't exist.
Please excuse the
All right, so number 22, a lot of students panic when they see a function like this. This is called the greatest integer function. And the big thing you should have learned about this in Algebra 2 is it is a step function. The picture of this is going to have steps, okay? And quite honestly, you don't really care where, all right? You just need to know that this graph is going to have some kind of steps. And most of the time, the steps are going to happen at integer values, okay? Like at the 1s and the 2s and that kind of thing. All right, so if you are looking for limits as x goes to 2, if it were just 2, okay, if it were a two-sided limit of any of these, it's not going to exist because you're pretty much guaranteed that there's going to be a gap. However, since this is a from the positive, all right, I need to look at putting numbers like 2.1 in, and that's actually the way I want to work this out rather than just putting 2 in. Now I can plug 2 in as well because this will work out. Now 2.1, if I plug it in, I'm going to get 2 times 2.1 minus the greatest integer not greater than 2.1. The greatest integer, which is a whole number not bigger than 2.1, is 2. And 2 times 2.1 is, what, like 4.2 or something? And so that whole thing is 2.2. Okay, so if I plug 2 in, I mean, you can't say the limit's 2.2. You would have to look at, like, plugging and then in 2.01, okay? But just try plugging 2 in. So 2 times 2 is 4. The greatest integer not greater than 2 is 2. The greatest integer not greater than 2 is 2. So your limit, it's just going to be 2 here. all of these greatest integer functions will have a one-sided limit. But you have to remember how to plug it in. Okay, if this was going to 2 from the negative, you would have to put in numbers like 1.9 and see what happens. So 1.9, 1.99, probably have to look at that. But guaranteed, if it were no plus or minus there, it would not exist. All right, so let's take a look at number 25. Now, we aren't given any limits now, okay? For the rest of the problems, we're not given any limits, and our directions for the rest of the problems are to discuss the continuity of the graph. So when I'm discussing the continuity of a graph, I'm going to look for some things. I'm going to look for asymptotes, okay, where the function is undefined, things that are not in the domain. Okay, those are going to be places where it's not continuous. So just looking at this graph, I can see by the graph that this is not continuous at x equals plus or minus 2. And that would be my discussion of continuity. It is not continuous at positive or negative, x equals positive or negative 2. That's it. Pretty simple. Okay, the graphs are nice because you can just look at the graph and say where it's not continuous. All right, so this is a piecewise function. I better look at the graph to see where it's continuous or not. All right, so first of all, where x is less than 1, I'm graphing the line y equals x. So when I put 1 in, I get 1. And that should be an open circle. When I put 0 in, I get 0. When I put -1 in, I get -1. So that's what this looks like. And then it's 2 when x is equal to 1. So right at 1, there's a closed dot at 2, but that's an open dot. And then it's the line 2x minus 1 everywhere x is greater than 1. But I'm still going to put 1 in there. Okay, when I put 1 in there, 2 times 1 is 2 minus 1 is 1, so that'll kind of close that in. And then when I put 2 in, I'm going to get, that's probably a bad place, but I'll move 2 to there. So when I put 2 in, I'm going to get 3. And so basically it looks like that. I don't think so, that's quite right. So I guess, is this continuous everywhere? I mean, it may look like it is, but in order to get that point right there, you're going to have to lift your pen or pencil. So this is not continuous at x equals 1. Regardless of the fact that that ended up being closed, and this line should probably have a little more slant than that one does, but gives you an idea. All right, next one. Now we want to talk about is this the continuity of this on this interval. This will probably extend to a third video just so I can give you more examples. So I want to find only if this is continuous on this interval from -1 to 4. So what I'm going to do is I'm just going to sketch a graph of this. It's not a big deal. This is a line, this is a line. So here I'm only going to put numbers 0 or less in. So when I put 0 in, I get 3. And that's a closed dot. When I put -1 in, I get 4. Basically, that's going to look like that. Over here, when I plug 0 in, I also get 3, so it closes it in. And then when I put 1 in, I get 3.5. So, it's just going to slant a little less. So between -1 and +4, is that going to be continuous? Yeah, it is. Okay, it's continuous everywhere on the interval. So being able to graph is an excellent skill to have. All right, so the next one, a cosine function. I don't really need to graph this one to realize that this is going to be continuous everywhere. 3x is a line. This is continuous everywhere. And cosine x is also continuous. So when you combine the two, a linear combination of these two, if you read the section, is continuous. So this is continuous everywhere. All right, that'll be it for this video. We'll have one more video.